back in Unit 1, when we started this course that we call chemistry, we were looking at matter. And I just gave you an introduction to matter at that point. And then in Unit 2, we looked at energy for a while. But now here in Unit 3, we're going to go back and revisit matter and look at it in a whole lot more detail. So just so you see where we're going in this unit, we're going to start out looking at the very tiniest particles that are inside the atom and how different combinations of those particles can make different atoms, which make different elements. And then we're going to look at what happens when we bring atoms together to make compounds. And then finally, we'll look at what happens when we bring compounds and elements together in different kinds of mixtures. But let's start out back at atoms. This is the periodic table, and hopefully you have a copy in your possession which you can access pretty easily. This is a list of all the elements known to man. In fact, we know that it's a list of all the elements that exist in nature because we found all of them in order. You see, each one of the elements is defined by the number of protons in its nucleus. And we have discovered the element that only has one proton in its nucleus, and that's hydrogen. And we've discovered the one that has two protons in its nucleus, and that's helium, and so on, all the way up through. And there are some atoms that are so big that they're not stable at all, and they just break down as soon as they're formed. But we've been able to make those artificially and see them, even if it's just for a microsecond or two. So we know that there are no more elements out there somewhere that we haven't found. So this is the list. Now the ones that I've outlined in pink are the ones that I'm going to be asking you to memorize the chemical symbols for. So let's just take a minute and go over those. I'll probably go through it too fast, so you may have to rewind the video and look at them yourself. So the first one is H for hydrogen, Na for sodium, Mg for magnesium, K for potassium, that's from the Latin name, Ca for calcium, Mn for manganese, Fe for iron, Ni for nickel, Cu for copper, Ag for silver, Au for gold, Hg for mercury, Zn for zinc, Al for aluminum, Sn for tin, Pb for lead, I for iodine, C for carbon, N for nitrogen, O for oxygen, F for fluorine, P for phosphorus, S for sulfur, and Cl for chlorine. So obviously there's lots more elements, and we'll be using many of those other elements this year also, but the ones that I've outlined for you are the ones that are the most commonly used, at least in this course. And there are also many of the ones that have Latin names, so that our English name and the symbol doesn't correspond very well. So for example, Au for gold, that's aurum, and Ag for silver, that was argentium. Pb for lead, that's plumbum. Plumbers get their name from that because they used to use lead pipes. Plumbers used lead pipes, and so we call them plumbers because Pb for plumbum meant lead, and so forth. So let's take a look at some of the things that all these atoms have in common. They all have in common basically how the atom is put together. And in the center of the atom, we have two different kinds of particles. So let's call these neutrons. I'll label them N for neutrons. And let's call these protons. And I'll just put plus signs in those because protons have a positive sign. Now actually, if I put one more neutron in here, I can actually make an element. That's a little lopsided. The nucleus ought to actually be spherical. But anyway, in the nucleus, we have all the mass, pretty much. The electrons have a little bit of mass, but almost all the mass is in the nucleus. Now, I want you to picture something. Picture a football field. So this is a very, very large field. Now picture the size of that football field kind of in 3 dimensions. So if you think of the length of the football field, now try to picture a sphere that has that length as its diameter. So this is a really, really large sphere that we're talking about. Now picture a dime right in the center of that sphere. So if we were going to draw the atom to scale, that dime would be the nucleus that's in the center of the atom, and the whole rest of that sphere would be where the electrons live. So you get a sense for maybe why we don't draw the atoms to scale, because we can't really do that on the board. If I tried to make the electrons only take up this much space, then the nucleus would be too small to see. So we never draw them to scale. But out here somewhere outside the nucleus, we're going to find our electrons. And for now, I'll just draw them like that. Now, you already know how to draw a Bohr model of an atom. And in the Bohr model, we don't actually show it's in the center. We just draw a little dot for that. And then if you remember, we have energy levels. Sometimes these are called the shells. So you may hear me talk about the shells. And we know that the first shell or energy level can only hold 2 electrons. And in this particular atom, remember these electrons are just flying all over the place. In this particular atom, we have 3 electrons, so I'm going to need the second shell, and we'll put another electron out there. So that would be the Bohr model for this. Now, if you look at your periodic table, we can identify what this atom is. We've already talked about this back in Unit 1, so let's remember how this works. You look for the number of protons, and the number of protons here is 3. And that's called the atomic number. And on the periodic table, we look for atomic number 3, and that's lithium. So we know that this is a lithium atom that I just drew. And we know some things about it. So let's do a little bit of vocabulary here. I'm going to erase this picture so that I have room to write it down. So what we've just defined, one thing was atomic number. And this is the number of protons in the nucleus. All right, now a second thing that we can define here is mass number. And this is like a count of all the particles that have some significant amount of mass. So this is going to be the number of protons plus the number of neutrons. So that's our mass number. So let's stop for a second and talk about what we mean by some significant amount of mass. Mass for tiny little particles like this is measured in something called atomic mass units, which kind of makes sense. It's a very, very, very tiny amount of mass. Sometimes it's abbreviated AMU. In fact, most of the time it's abbreviated AMU because nobody wants to write out atomic mass unit all the time. And one proton has a mass of 1 AMU, and one neutron also has a mass of 1 AMU. Now here's the symbol for proton. I haven't introduced that before. P for proton and the plus sign to designate that it has a positive charge. So a proton has a mass of 1 AMU, and a neutron, designated with an N and a little 0 because neutrons don't have any charge, is also equal to 1 AMU. So let's talk about why we don't count the electrons when we're trying to talk about mass. Each electron has a mass of about 1 over 1800 AMUs. So they're so tiny that they don't really add anything significant to the mass. So when we're thinking about the mass of the atom, we can just kind of ignore them. So the symbol for an electron, E for electron, with a little negative sign so that we remember it has a negative charge. So there's the masses of the little tiny particles that make up the atoms. There's also the charges of the little tiny atoms that make up the particles. So positive charge for a proton, negative charge for an electron, and no charge at all for a neutron. And our protons and our neutrons live in the nucleus of the atom. That's the dime in the middle of the football field size sphere. And the electrons are whizzing around the outside, so they can be, I was going to say anywhere. They can't actually be anywhere. There's rules for where they can be, but they will take up that space, and they will be moving very, very fast. So fast that even if you could see things that small, you wouldn't be able to see them. And sometimes we call it an electron cloud because the electrons are just buzzing around in there so fast that they kind of give that whole big area a negative charge. All right, so let's look at a couple of other vocabulary words. Get this off the board here. So we've got atomic number and we've got mass number. And now we have something else called atomic mass. And in order to talk about that, we also have to talk about isotopes. So let's start with the isotope. And it doesn't make a whole lot of sense to talk about isotope singular because isotopes are only important if there's more than one of them. Some of you may have siblings, and it doesn't make a whole lot of sense to talk about a sibling unless there's more than one of them. So you are siblings to each other, that's how you're related. Well, isotopes are a little bit like that. They're different forms of an element. So remember that the identity of the element only depends on how many protons are in the nucleus. But sometimes there can be different atoms that both have the same number of protons in the nucleus, so they are the same element, but they don't have the same number of neutrons in the nucleus, and so they will have different mass numbers. And we will call those isotopes. So they are both isotopes of the same element. That's how we would say that. So in nature, all the elements have more than one isotope. Usually, there's one isotope that predominates. It might be like 99% of all the carbon out there has a mass of 12. But there's some 1% that might have higher mass. In fact, there's an isotope that's called carbon-14 that has a mass of 14 instead of 12. So maybe we should look at that as an example for carbon. So an isotope is one form of an element. Different isotopes of the same element have different numbers of neutrons, but of course the same number of protons. So if we think of carbon as an example, we can talk about symbolism here a little bit. Carbon will always have 6 protons. And if you were going to write the complete symbol for that, you'd write a 6 over here. Now, most of the carbon in the world also has 6 neutrons. So that means that its mass number would be 12, because it's 6 protons and 6 neutrons. So I would write a 12 up here. So mass number, we've already talked about that. Now, let's say that we have this other isotope of carbon that also has 6 protons. Now, you see that this information is kind of redundant. If we know it's carbon, we know it's 6, but sometimes we put it there just to remind ourselves so that we can do the math. Now, let's say that we have carbon-14. So carbon-14 is a radioactive form of carbon, and they often use it for carbon dating. So this one has 8 neutrons in the nucleus, and this one has only 6 neutrons in the nucleus, so they have different masses. Now, atomic mass, which by the way you find on your periodic table, if you have your periodic table, you can tell that there is one number that is just, well, let's use carbon since I started talking about that. One number that's usually above the element, not always, but in this periodic table it is, and this one is 6 for carbon. But down under that, it says 12.0, let's see, this one says 12.011. That is a weighted average of the isotopes of carbon that are found in nature. And when I say weighted average, we mean that we might multiply the 12 by 99% and then multiply the 14 by 1% and then add those together to get the atomic mass. Now, I'm not entirely sure that there are only 2 isotopes of carbon, so if you do the math and it doesn't come out to 12.011, don't be surprised. But that's the idea of how these things work. The atomic mass is always a weighted average of the different isotopes that are found in nature. So since we know that most of the time there's one isotope that predominates, if you take that atomic mass number and round it off to the nearest whole number, you'll have the mass number of the most common isotope. So anyway, let's define atomic mass here and then we can try a few examples. So atomic mass is a weighted average of the masses of the isotopes found in nature. And they're weighted according to their abundance. So let's take, for example, oxygen. So if you look at your periodic table and you see oxygen, you'll see 15.999, which is really close to 16. So one can assume that in the case of oxygen, the most common isotope has a mass number of 16. Now oxygen happens to be number 8, so that tells us that there's 8 protons in the nucleus. And if the most common isotope has a mass of 16, 16 minus 8 is 8, so that means there's 8 neutrons in the nucleus also. Now I don't want you to get the impression that the number of neutrons and the number of protons is always the same, because that's not true. So let's look down at something like gold, 196.97. So 196.97 represents the total mass of the nucleus. So let's just call that 197. But if you look at the number of protons, it's only 79. So 196 minus 79 tells you the number of neutrons. So the number of protons in this case is not the same as the number of neutrons. So let's take some examples. And I will sneak in another concept while we're doing this. Let's take the example of chlorine. And let's say that we can tell from our periodic table that chlorine has 17 protons in its nucleus. So 17 would go down here. And if you look at the atomic mass, you're going to see it's 35.45. So this one is not particularly close to a whole number, is it? So this tells us that there's probably 2 isotopes that are in pretty close to equal abundance here. So let's pick the isotope. Let's see, 35 minus 17, and I can't do math in my head, so 18. All right, so let's say that we have 18. Well, let's see, we'll put 35 up here. So here's what I would like you to be able to do. I would like you to be able to, first of all, use your periodic table to find the number of protons. Use your periodic table to find the most common isotope. And if I was going to give you an example, I wouldn't pick one that wasn't close to a whole number. So if you have this number and this number from your periodic table, what can we do? We can say protons, neutrons, electrons. Make a little chart here. And the number of protons easily found from the atomic number. The number of neutrons would be the difference between these two. So that would have to be 18, and then if I add them up, I get the mass number. And then the number of electrons, how about that? Well, this is a neutral atom, so we're going to say that the number of electrons has to equal the number of protons, because a negative charge and a positive charge cancel each other out, and so we'll end up with a neutral atom. So whenever you're told that you have a neutral atom, you know that the protons and electrons are there in equal numbers. But what if you don't have a neutral atom? What if, let's get rid of that for a second. What if you know that you have chlorine with a -1 charge? What do we do then? Well, we think to ourselves, that must mean that there's one extra electron. So there's enough protons to cancel out most of the electrons, but there's not enough protons to cancel out that one last charge. So in this case, we can say the 17 protons, because that will not change. It will not change. As long as it's chlorine, it has to be 17 protons. Neutrons, we're not changing the mass here, so we'll keep that the same. But electrons, we'll say there must be 18 electrons there, because there's an extra one, and that's why it has a negative charge. Now let's change the scenario and look at sodium. So sodium is number 11, and it has 11 protons in its nucleus, so we can right away put that there. And then if you look at your periodic table, you will find that sodium is 22.99, pretty close to 23. So we will say that the mass number is 23. So that means the number of neutrons, 23 minus 11, must be 12. So what do we know about electrons? Well, there's no charge right here, so the electrons and the protons must be the same number. So we'll put 11 over here. A little OCD. However, sodium very often exists like this. It's a positive ion. And a positive ion has one extra proton. Now what that means is that it lost an electron. It does not mean it gained a proton. If for some reason it was able to gain a proton, well, for one thing, that would be a nuclear reaction, and that would be crazy energetic. But if it was able to gain a proton, it wouldn't be sodium anymore. It would be magnesium. So if the symbol says sodium, we know that we still have the same number of protons as this sodium, so we still have 11 protons. And we haven't changed the number of neutrons either. But we have changed the number of electrons. This time we've lost an electron so that there's an extra proton. So there's only 10 of these. So if I have one extra proton, I'll have a positive charge. If I have one extra electron, I'll have a negative charge. So that's how you can figure out the charges on the ions. Now, what if you just have a periodic table and you don't know what the charge on the ion ought to be, but somebody asks you, if this formed an ion, what would the charge be? Well, I will tell you. As it happens, everything in group A, when it forms an ion, will form an ion with a +1 charge. Now, there's some good reasons for that we will talk about another time. Everything in group 2A will be a +2 charge. Everything in group 3A will be a +3 charge. And then we stop. The elements in group 4A usually don't form ions, and the elements in group 5A might form ions, but they don't that often. Usually they are inclined to share their electrons instead. So let's skip over to 6A. And in 6A, they will usually have a -2 charge. In 7A, they will have a -1 charge. And in 8A, again, they don't form ions. So the ones that I would like to have you remember are these. And another time we'll talk about why that happens that way. But for now, I just want you to remember that it does happen that way. So if you were to look at a periodic table and you were to find sodium and you found that it was in group 1A, you would know that if you're asked about an ion, you would say, that's going to have a +1 charge. That means it lost an electron. So that means it has 11 protons, but only 10 electrons. And you can figure all that out all by yourself. And I think that takes care of it for section 1.